All right, so today we're going to do a sort of a basic run through about semiconductors and its relation to band theory, which is kind of a extension on what you know about molecular orbital theory. So something that you learn very quickly in general chemistry is that metals have a property about them that create these whenever you have like any solid metal, it forms this sort of sea of electrons, as shown over here. And these electrons are moving around in sort of a non-directional way. And if any sort of charge is acted on this piece of metal, you can make these electrons move in a specific direction. This is why metals can be very conductive, because they have already free-flowing electrons that can be moved in any sort of direction that is necessary. So this is kind of where molecular orbital theory starts to fall apart, because even though molecular orbital theory does account for how electrons are where electrons are based on the amount of energy that is required for a bond to occur, it doesn't really account for this movement of electrons, which is what is covered by band theory. So what I've shown you here is an energy diagram of any metal that is considered a conductor. And here what you see is that this progression is an adding of a number of metal atoms. So here you would just, for example, if we were looking at copper, this would just be one little copper. And whenever you put two coppers together, you get a bonding orbital and a non-bonding orbital, where these electrons are, by MO theory, would be shared in one space. Now, as you start to add more coppers, so this would be copper 4, and this would be copper 8, and so on and so forth, what you start to see is that these s orbitals that start to get filled start to create a range of energies where these electrons and these non-bonding orbitals are sort of forming, until what you start to see is that a band begins to form, where you have a band of molecular orbitals that are occupied with electrons, and then a band of unoccupied non-bonding anti-bonding orbitals. And what you see in conductors is that it doesn't take very much energy for these electrons to just move straight up into these unoccupied orbitals. This is what makes conductors so good at transferring electrons, is because they have this giant range of unoccupied orbitals where these electrons can easily move into. Insulators have the same idea, but as you can see, there's this huge energy gap between these two, between the unoccupied orbitals in blue and the occupied orbitals with electrons in yellow. And because of this energy gap, it's very difficult for these electrons to move. You would require a lot of energy to try to push these electrons up into these unoccupied orbitals, and it's just very efficient as a result of that. So that's the difference between conductors and insulators. Now, what I've shown here are the band theory diagrams of semiconductors. Now, first we're going to look at the one on the far left. Semiconductors are your metalloids, and in this case we're looking at silicon, which is used a lot in modern technology, your computers, your phones, stuff like that. And it is a very useful element, because it kind of semiconductors fall in between conductors and insulators, where it does have a significant energy gap where energy is required to be inputted in order for these electrons to move up, but it's not nearly as much of a gap as insulators. So this is useful if you think of it in terms of an on and off switch, to be able to control this gap and how these electrons are moving can be equated to how you would think of an on and off switch, being able to, the amount of energy required to push these electrons. So here we have a normal semiconductor of silicon crystal. And as you can see, silicon has 4 valence electrons, so it's going to connect similarly to carbon. And these electrons are going to just sort of pass through these bonds that have already been formed. Now, there are different types of semiconductors. And these semiconductors sort of increase the efficiency of increasing the conductivity is essentially what I'm getting at. In this case, there are 2 different types. You have your p-type and your n-type. So first we're going to look at our p-type. So in order to increase the efficiency and the conductivity of a semiconductor, you can introduce other substances into the crystal. In this case, for example, we have doped it essentially with boron. And what you can see is that boron has 3 valence electrons. So whenever it connects to the silicon, whenever you break apart the crystal, add the boron, and then reform the crystal, what you're going to see is this boron is going to form 3 bonds with 3 different silicons, but it has one little gap in between. As you can see from the Lewis structure, it doesn't connect to another silicon. It kind of leaves this little gap in between the crystal. This gap is referred to as a hole. And what happens is, because you have this hole form, it creates a sort of area of positive charge, because whenever you're looking at the flow of electrons, if you're looking at an area with a lack of electrons, you can consider that a positive area. And this is going to increase the flow of electrons through the system. So these are your p-type semiconductors, because P stands for positive, because it's creating a positive area. Opposite of that, we have our n-type semiconductors, which also increase the conductivity of semiconductors. In this case, our dopant is phosphorus, which has 5 valence electrons. And if you reform the crystal adding phosphorus as your dopant, what you end up with is phosphorus will connect 4 different silicons, but it will have 1 remaining electron. And this kind of creates a field of negative energy. And as a result, you start to see a movement of electrons through the structure. Now, connecting this to what we learned about band theory, as you can see in a normal semiconductor on the far left, you have your unoccupied orbitals in blue and your occupied orbitals in yellow, and there's an energy gap between these 2. If you look at your p-type ones, however, what you'll notice is that a new little area of space is created where it sort of inserts in between the gap an acceptor level of space of orbital, where you can have these electrons from the occupied levels to just jump into this unoccupied space that we refer to as a hole or a gap. This will, as you can see that I've indicated here, it makes the energy gap between the unoccupied and the occupied orbitals smaller than it would be in a normal semiconductor. Looking at the n-type semiconductor, the same thing. As you can see, there's a donor level in this case, as opposed to an acceptor level that is added in between these 2 occupied and unoccupied orbitals. And what you can see is that this extra electron that is in this phosphorus, and consequently in all the other phosphoruses, can be moved easily into this unoccupied orbital as a result of this donor level being added. And as you can see again, it decreases the energy gap between the two levels. So this is how semiconductors can be explained through band theory, and how p-type and n-type semiconductors increase the efficiency of semiconductors and why they are able, kind of a rationale as to how they do it. Okay, thank you for watching. I hope this was a helpful explanation of these concepts. Yeah, thank you for watching.